So welcome everybody. It's 11:10 in the morning. I can see 357 of you awake and alive, and I'm so happy you're here, and I'm very proud of you for showing up and paying attention to physics and learning some physics this semester. I think these are pretty difficult circumstances to learn physics in. When you're looking at your professor on a little Zoom screen and you've got other screens going on, and I realize that you've got Facebook over there and you've got Discord up there, and I'm this little guy talking in the middle, so I appreciate you being here. Let me share my screen and we'll talk about what's on the agenda for today. So you can see the ideas there. Make sure that's my participant list. And chat. Oh, there it is. Okay, I can see. Yeah, so I'm going to finish up by doing an example, finish up chapter 6, doing an example on collisions in 2D. And then I'm going to talk about work and energy, and conservation of energy, which is starting in chapter 7. Even though chapter 7, you won't actually see this on a midterm till midterm 4. It won't be on tomorrow night's test. But I wanted to start in on it today. But let's get going. Actually, I want to start things with a pull. Now, this is actually a numerical pull. So the question is, you've got a 1 kilogram block, which has dropped from a height of 1 meter above the floor. When it collides with the floor, it takes 1 millisecond to come to a complete stop. This is an inelastic collision. Okay, so, and I can make a note there, I guess, that delta t is equal to 1.0 times 10 to the minus 3 seconds. That's what a millisecond is. Right? The question is, what was the magnitude of the average force of the floor on the block during the collision? And I've given some numerical answers there. It's not I don't usually do this to you, especially on a Monday morning, but this is a good chance to try to see if you can do this in a reasonable amount of time. So definitely leave some time to answer questions more about the midterm. But this is the kind of question you're going to be getting tomorrow night. Okay. So it's been a couple minutes since I started this. I'd like to end the polling. Let's give you another 15 seconds to click in and answer, and then I'm going to discuss it. Okay. So as you can see, I've already started trying to work this out. This has got two segments of motion. The first segment is the free fall of the block, accelerating towards the floor. And the second segment is this collision, which it's told you takes a delta t of 1 millisecond. So it has to, so just before it hits the floor, it was still in free fall. When it's hitting the floor is a little bit bouncy. I guess it pushes it over a certain amount of time, or maybe the block compresses. But over this 1 millisecond, it has to push enough force to completely stop it. So you've got a free fall problem followed by a conservation of momentum kind of problem. So I'm going to cut off Pauling. Was kind of spread around. C was the most popular answer though, followed by E and then B. Okay. Maybe you weren't really expecting this first thing on a Monday morning, so that's fine. I'm going to use equation 2.7, actually from chapter 2, which was that 2 times A times that distance, which I'm going to call H, is equal to V final squared minus V initial squared. So V initial, and let's call this for segment 1. So V initial for segment 1 equals 0, because we're going to assume that it's dropped from rest. It's dropped from rest. Doesn't exactly say that. And so V final of the first segment is the square root of 2 times G times H. So I plug that into my calculator, times 1.0. And I got V final 1 is 4.43 meters per second. And what goes on here is V final of segment 1 is V initial for segment 2, which is again 4.43 meters per second. So just before this collision with the floor, the block is moving downwards with a speed of 4.43 meters per second. Then it has to stop. So what you do is P initial in the y direction, let's define plus y is down, for example. Then you've got P initial y plus the impulse from the floor is equal to P final y, which is equal to 0, right? So you've got m times V initial of the second segment plus F sub y times delta t equals 0. So you're asked for the absolute value or the magnitude of the force. It's going to be the mass times the V initial of the second segment divided by delta t. So it's 1.0 times 4.43 divided by 1 times 10 to the minus 3. And I got 4,400. So actually, yeah. And so if you used, 10, just 1 second and didn't 1 millisecond, probably would have got B. Okay. I said I wanted to do an example of this 2D collisions. So I think that's next on the list here. So this is an idea that you are a police officer and you've just arrived at a crash site and you're investigating. Maybe you're a detective. And what happened was, you know that there was a yellow Hummer with a mass of 3,900 kilograms. It was heading southbound to an intersection, and it collided with a Toyota of mass 1,200 kilograms, which was driving east. And by the way, the speed limit in Toronto is 50 kilometers an hour. After the collision, the two cars stuck together and the combined mass skidded along the ground. So you got out your tape measure and actually measured the skid marks to have a length of 10 meters. And you were able to find, get your protractor and realize that those skid marks went at 32 degrees angled east of south. And you know that the coefficient of kinetic friction, you look it up in a table between rubber and dry pavement, because it was a dry day, is 0.8. So the question you have is, who's at fault here? How fast were these cars going just before the collision? And who's at fault? So what you're going to do is you're going to assume that there's no external impulse during the collision. This is how you can conserve momentum. Okay, so that the P initial is equal to the P final. because there's no J from outside things. So the initial situation, we can sketch that, is going to be, you've got your Hummer, H, which has a mass is equal to 3,900 kilograms. And its Vy is equal to question mark, but it's negative. So what I'm going to do is define that plus y is north and plus x is east. So this is north and x is east. Okay. And then, so that's going down, and then it's going to collide, is destined to collide with this Toyota, which has the mass of the Toyota is 1,200 kilograms. And Vx here is question mark, but you know that that one's positive, going in this direction. That's your initial situation. Your final situation is going to be that they're kind of collided together. So I'm going to draw them kind of like this. Whatever they were, this is now what's called in the question the combined mass. Okay, so MCM, I'm going to call it combined mass, CM, is the mass of the Hummer plus the mass of the Toyota. Which is equals. Okay, and then this thingy is going at some speed, V final, of the collision is going to be in this angle theta here. Theta is equal to 32 degrees, and that's measured to the east of south. And this idea here, the big idea, is that kinetic friction causes the combined mass to slow as it skids. So if it starts like this, with some V initial, then it's going to go this distance, D is equal to 10 meters, and then it's going to stop. V final is 0. So V final of the collision equals V initial of the skidding. There's two segments of motion. You've got to keep track of it. So let's call it two segments of motion. We call it 1 is going to be the collision, and 2 is going to be the skidding. So, and the idea is V final of 1 equals V initial of 2. That makes sense. So, and I think I want to start. Let's start by doing segment 2, by analyzing segment 2, using the stuff that we've learned from previous chapters. So we can do a force diagram of the combined mass. So if this is the combined mass, you've got the normal force of the road on the combined mass. You've got the friction, kinetic friction of the road on the combined mass. And then you've got the, I guess, the force of gravity of the Earth on the combined mass. And we're going to define, I'm going to define y in this case as up, and d, I guess, is the distance that it's traveling. So this is a diagonal distance. But basically what you're doing here is you're saying that the sum of the forces now, and maybe I should call it z actually, because it's getting confusing, right? Because we've also got y as being north, right? So let's call this z and d. Some of the forces in the z direction, which is actually vertical, is going to be 0, because it's not accelerating up or down, which is the normal force minus mcm times g. So you know the normal force is equal to the mass of the combined mass times g. The sum of the forces in this diagonal direction, d, is equal to negative mu sub k times n, which is negative mu sub k times m cm times g. So it's going to be accelerating towards the left. This acceleration in the d direction, I guess, is going to be equal to the sum of the forces in the d direction divided by the mass combined mass. So it's going to be equal to negative mu sub k times mcm times g divided by mcm, which is nice because the mcm's cancel. And then I'm going to use, again, equation 2.7, the one we used before, which is that 2 times A times D is equal to V final squared minus V initial squared. So the skid stops when the combined mass has a final velocity of 0, right? So this goes to 0. And you get the V initial is equal to the square root of negative 2 times A sub D times D. So that's in there, plugging in our equation, you've got the square root of 2 times mu sub k times g times d, things that you've measured. So, so now we have this collision, the second segment, which it's going to have two things. You're going to have the x and you're going to have the y. The x is that p initial x plus the impulse equals p final x. And so if you want to kind of draw that out with energy bar or momentum bars, then you're going to have that if this is the Toyota and this is the Hummer, the Toyota was going in the x direction, the Hummer was not. There's no external impulse, and you get the p final in the x direction is equal to the combined mass is equal to just the Toyota. And then P initial Y plus the impulse, external impulse in the Y direction is P final Y. So once again, this is the Toyota, and this is the Hummer, and this is the external impulse, which is 0. Just drawing your momentum bars. You've got the Hummer was going in the plus Y, or actually was going in the negative Y direction. Let's get this right. These up. The Toyota was 0, the Hummer was negative. There's no impulse, and so you're going to have a negative y. This is the Hummer. Okay, anyway, what you want to do is represent mathematically. So you've got the mass of the Toyota times the V Toyota initial plus 0 plus 0. You're trying to find the initial speed of the Toyota equals the mass of the combined mass times V final, which we had from before, times sine theta. That's equation 1. And then the y equation is that you've got 0 minus the mass of the Hummer times its initial velocity, which you'd also like to know, plus 0, is negative combined mass times v final times cos theta. That's equation 2. So equation 1 tells you that v Toyota initial is equal to the combined mass divided by the mass of the Toyota times, we can actually get the v final from here. It's the v initial of the skidding phase. So it's 2 times mu sub k times g times d times sine theta. And the second equation for the y component tells you that the velocity of the Hummer is v cm over v m cm divided by m Hummer times 2 mu sub k times g times d times cos theta. Okay. We're almost done this. So now we just plug in the numbers. Vt initial is equal to 1200 plus 3900. That's the combined mass divided by 1200 times the square root of 2 times 0.8 times 9.8 times 10 meters per second, or 10 meters times sine of 32. This is what you measured, and you were able to tell that before the collision, the Toyota must have been going 28.2 meters per second. Okay. And then similarly for the Hummer, it's equal to 1200 plus 3900 divided by 3900 times that same square root, 2 times 0.8 times 9.8 times 10 meters times cosine of 32. And I plugged that in and I got 13.9 meters per second. So again, going back to from the police officer's point of view, first thing that you know is that the Toyota was going much faster than the Hummer. So that's not good. I don't know what color the light was, but you can actually right now just say that the V Toyota initial, remember it's 28.2 meters per second. So if you times that by 60 minutes, 60 seconds per minute, times it by 60 minutes per hour, and times it by 1,000 meters. I get it in kilometers on the top, right? So 1 kilometers per 1,000 meters. Then we get seconds cancel seconds, minute cancel minutes, meters cancel meters, and you end up with, plugging that all in, V Toyota equals 102 kilometers per hour. And it was already established that this is in a 50 zone. So in a 50 kilometers per hour zone. So I would say Toyota is at fault. Okay. Josephine?
Hi, can you go back to the slide, the sketch and translate one?
This one?
The one before.
I mean, I just said that there's.
So, why is the angle where it is? Like, how do you know that's where to draw it?
Well, it says in the question that the police measure that the skid marks are a line 10 meters long angled at 32 degrees east of south. So you start from south and then go 32 degrees east.
Oh, okay, thanks.
And then econ.
Professor?
Hi.
Are there any practice we can do for the midterm 3? Like the previous two, we all have the practice midterm.
Yeah, good question. So I haven't put on any extra problems at this point. I mean, I've got the homeworks, right? So you have those. Heyman, did you have a question?
Hello, Mr. Harlow.
Hi.
So I have just a question. Can you go to the latest slide? Like,
For the answer?
yeah, do you have like latest slide?
Yeah.
The next one. Okay, thank you. So in the left down side of your whiteboard.
Yeah.
Just curious. Well, we learned that P equals mv, right?
Yeah.
So I'm just curious, like in the left down side of your equation, why is say since it is m times v, like you said v equals, in this situation is square root 2 mu gd, and like why is v also equaling like mv? Shouldn't that left side big V should be p?
Yeah, but so I did that. So but I divided by both sides by mt, right? So for equation one, it's m of the Toyota times its initial velocity equals the mass of the combined mass times its velocity right after the collision. And then I divided both sides by mass of the Toyota. So you got mcm over mt. Do you see that? I'm just equating momentums, p, but then I divided both sides by m.
Yeah, it like mv equals p, so like I thought like left side would be p.
Well, but I divided by m.
Oh, so m's unit, something like kilogram disappear. So
Yeah, I divided both sides by m because I'm solving for v, right? The thing I really care about, the cops care about the speeds of the car just before they crash.
right, you divided the units. Oh, okay.
see?
Thank you.
Yeah. Okay. So I'm going to keep going and kind of get on my way into chapter 7, I think. So the big ideas of both chapter 6 and chapter 7 is introducing these conservation laws, and they're very, very fundamental in physics. I would say a lot of people would say there's nothing more fundamental in physics than conservation of energy, okay? And conservation of momentum is probably in second place. These concepts give us useful ways of analyzing motion, and they're useful, for example, even if you talk to people about the Large Hadron Collider where they're colliding protons, the first thing they do is they have to conserve energy, right? Energy and mass. So some quantities stay the same while other things around them change. For example, there is something called conservation of mass. If you take a dish and you throw it on the floor, you assume that the initial mass of the plate should equal the masses of all the pieces. So if you go around and pick up all the pieces of a smashed plate and you put them on the scale and they weigh less than the initial plate did, then you can actually infer from that there must be some more pieces somewhere. You can look under the stove or something like that. So we believe in these conservation laws, and they allow us to make predictions and solve problems. So in this chapter 6, we had conservation of momentum, P initial equals P final, and that's true if the external impulse is 0. And now we have conservation of energy, which is going to be that the initial energy equals the final energy if the work done in the system equals 0. So what is energy? Energy is a property of an object, okay, like age or height. Every object that is moving has some kinetic energy. Okay. Also, an object that's in a gravitational field, you could say has some gravitational potential energy. We call that U. Energy has units and can be measured. The units are called SI units. They're called joules. They have their own special name. Energy is relative. For example, the kinetic energy of a car driving by on the highway is different if you're sitting on the side of the road watching the car go by than it is for someone who's actually sitting in the car. Because if you're sitting in that car, the car is at rest relative to you. So kinetic energy is relative to the observer. So here's an example of a car, and there's an equation for kinetic energy. It's 1/2 m times v squared, where v is the speed. Okay. And so we actually we can find out there that the units, we'll look at them, are kilograms times meters squared per second squared equals joule. Just from that equation. We also have another equation for the energy of position, gravitational potential energy. So here we have the behemoth of Canada's Wonderland. It's up at the top of the hill. It has some y position, y, okay? And so it has some gravitational potential energy. It may be at rest right now and not moving, but if it goes down to y, if this is y initial, and this is y final, is 0 or something, then it's going to lose a lot of gravitational potential energy, m times g times y. Here's g is equal to 9.8 meters per second squared. And so let's actually check the units. You've got kilograms times meters per second squared times meters equals kilograms meters squared per second squared. So that's actually the same as it was for kinetic energy. So that's good. That's a units check. What else do we have? Oh, there's also spring. So this was introduced in chapter 7. The energy of position, elastic potential energy of a spring. U sub S is spring. elastic potential energy. When you compress a spring, it gains elastic potential energy. So X is the distance, the end of the spring is pushed or pulled past equilibrium. And we'll talk more about this in a bit. And this thing K is called the spring constant. Just want you to know that there's something, if you have a loaded spring, it has some potential energy as well. Internal energy. So this is the energy of microscopic thermal vibration. So this lava has a whole bunch of internal energy because it has a high temperature. It's proportional to the temperature. So something that's a higher Kelvin temperature. So this proportionality works for T in degrees Kelvin, if you've ever heard of that. If you ever want to know why scientists use degrees Kelvin so much as degrees Kelvins, is because that's when you get this proportionality of temperature and internal energy. So I've got a little demo that I wanted to do. It's about dominos. So a domino is a rectangular solid which can be balanced on its edge. When standing upright, there's gravitational potential energy, which is at a maximum. And if it's lying down, gravitational potential energy is less. So this is a position of unstable equilibrium. Even a small little perturbation can cause a domino to start falling and releasing its gravitational potential energy and converting it to kinetic energy, which can then tip over another domino. So you can get a chain reaction. So I've got some dominoes. Let's actually stop my share. Now I want to take your camera. Bye. So here I have a bunch of dominoes. And what you might not know about dominoes is that a domino, when it tips over, can knock over another domino that's 1.5 times bigger than the previous domino. So this is a sequence of dominoes, and each one is 1.5 times bigger than the one right next to it. The smallest domino is just about 1 centimeter tall. Sort of see it there. I have to hold it with these tweezers and very carefully put it down without knocking all these over. Okay. The biggest domino, you go up the thing, is over 1 meter tall, and it is over 100 pounds. So I put a lot of force into that, do a lot of work on that, and push that up. And now I'm going to start the chain reaction. You guys ready? Okay. 1, 2, 3. Okay, I think they felt that one in the next room. That's a chain reaction. So what happened there is that I put in a tiny little bit of input energy with my tweezers, knocked over that first domino, which then knocked over the next one and the next one and the next one until this huge amount of energy was released. But of course, I put all that energy in there when I first pushed those things up and stood them up on their end, giving them a lot of gravitational potential energy. So all I did was release that stored gravitational potential energy and convert it into kinetic energy of falling and the sound energy when it collides with the floor and all that stuff. This is just showing how you can store energy. And hopefully it woke you up a little bit too. Okay. screen. Get on my Zoom settings right. Find my chat. Participant Q&A. Okay. Someone was asking about the significant digits. Can't remember. I have to check that. Actually, Catherine, did you want to ask a question? Your hand's still up.
Hi, it's a question about the question that you solved right at the beginning in the midterm. Would we be expected to solve a question that long on the multiple choice midterm tomorrow?
Yes, yeah, definitely. So you mean the first one, not the second one, right? That first one on this one?
No, the one that had all the steps with the
Yeah.
cars.
No, that's a little long. So I make
Okay.
some kind of portion of that. Yeah, I agree. Yeah, that would be too long to have 1/10 of the midterm. Yeah, that's a really.
But that would be something that if this midterm was a 2-question problem, this question
maybe yeah
would be applicable to that kind of thing.
It is a little involved. Obviously, it took me 1, 2, 3, however many whiteboards to go through it. I think it's interesting. This is a bit of more of an interesting question because it's you're a police officer investigating sort of real life. But I do think there's maybe too many steps to cram it into a half-hour midterm. But this one definitely you should be able to do.
Yeah. Okay. Thank you.
Sure. And Ojas, you have a question? Can't hear you. And Rohit.
Hi, Professor.
Hi.
So what is where would objects reach an unstable equilibrium? When would that happen?
So good question. So anytime there's a situation where a small perturbation makes the potential energy decrease, that's called unstable equilibrium. So the way we sometimes do it is we make a plot of your potential energy versus position. So if this is position, and this is potential energy, which is sometimes called U, and I could call it U sub G. If it goes like this, then that's stable equilibrium. If you move either way, you're at the bottom of a hill, I guess, and so the gravitational potential energy increases, and then you just roll back to the middle. That's called stable. And I'll talk more about this a little bit later. It does come up in the book. If it goes like this, which is the case for the domino, U sub G, where you push it in either way. If you tip it this way, the gravitational potential energy goes down. If you tip it this way, the gravitational potential energy goes down. Doesn't matter which way you tip it, you're converting energy into kinetic, and so it rushes away from equilibrium. So this is called unstable. Great question. And that kind of goes into next. Okay, so one of the most basic forms of energy is called work, and it involves force and distance. So basically it's force times distance. So in equation form, we have work is F times D times cos theta. What does that all mean? So theta is the angle between the force and the displacement. So there's two things that are going to have to occur, and I'm going to give some examples of this when you're doing work. First of all, you have to apply a force. And second of all, the thing that you're applying a force on has to move. In which case you say that you're doing work on the object. And so another, SI unit of work is the Newton times the meter. This also equals the joule. I don't know if you remember that in Newton, for F equals ma, the units here are going to be that the Newton is equal to the kilograms times meters per second squared. So a Newton's times a meter is going to be kilograms times meters squared times divided by seconds squared. So that's a units check. Again, that's a joule. So there's three situations here with this briefcase. Let's say your hand pulls a briefcase to the right and moves it to the right. So what you've got is the force and the distance are in the same direction. So this means you are helping the motion with the force. So the work that you do on the object is positive. The force is adding energy to the object in the environment or whatever. The force is maybe speeding up the object. But the point is that work, which is equal to F times D cos theta, in this case, theta is equal to 0. It's the angle between F and D. And so cos theta equals +1. It's hard to draw that. It's the angle between F and D. Okay. If your hand supports the briefcase with an upward force and the briefcase is moving towards the right, this is a case when the force and the distance are at right angles. You're not helping the motion with the force. So the work is 0. The force is not changing the energy of the object. It's just supporting it in this case. Okay. So the force, another way of saying it is you're not speeding it up or slowing it down. Want to look at the equation, work equals F times D times cosine theta. In this case, if the force is up, D is that, then the angle here is equal to 90 degrees. So cosine of 90 degrees is equal to 0. Lastly, if your hand is pulling a briefcase to the left, but for whatever reason, the briefcase is actually moving to the right, maybe it was already moving to the right and you're trying to slow it down, you're trying to break it or something like that. This means that the force and the distance or displacement, are in opposite directions. So you're hindering the motion with the force. So the work done on the object is negative. The force is reducing the energy of the object. Maybe it's like slowing the object down. So once again, if you look at the force equation times cosine theta, if this is D to the right and F is to the left, then this whole angle theta is 180 degrees. It's a 180. And it turns out that the cosine of 180 degrees, is equal to -1. So work equals negative F times D. So let's actually try to do a couple poll questions here. I haven't done a lot of these yet today. Justin is doing a bench press and he slowly pushes the bar up a distance of 0.3 meters while pushing up on the bar with a force of 200 newtons. The bar moves with a constant velocity during this time. So during this upward push, how much work does Justin do on the bar? Is it A plus 60, B plus 120, C 0, D negative 60, or E negative 120? Okay. Let me just click in, give you another 5 seconds. And in polling, so 77% of you who voted were saying A, that you've got a plus 60. So I like it. I think it is A. That's going to be the work is equal to, you got in this case, the force of Justin on bar is up. The displacement, D of the bar, is up. So you're going to be F times D, so theta is equal to 0. So it's just going to be your 200 newtons times your 0.3 meters. And so that's going to be equal to 60 joules. The same question now. Let's relaunch the polling. So in this case, he's slowly lowering the bar down a distance of 0.3 meters while pushing upwards with a force of 200 newtons, and the bar is moving at constant velocity. Can you picture that? If you're pushing upwards on this thing, you're just lowering it down the distance of 0.3, but you're pushing upwards. If you just let go, it would fall on you and accelerate, but you're lowering it slowly. How much work does Justin do on the bar in this case? Okay, let's give you 10 seconds to click in, please. And survey says, so most people are saying D negative 60 meters, so, or 60 joules. So that's exactly correct. So what's going on here is that, again, if this is the force of Justin on the bar, and the distance is D is down, then theta is equal to 180 degrees. Okay, so work is equal to negative F times D. And so when he's pushing up, he's adding energy to the bar. He's increasing the gravitational potential energy of the bar. It could fall. If he's lowering it down, then he's actually reducing the gravitational potential energy of the bar. He's doing negative work on the bar. And then lastly, well, I'm not going to do the polling on this one. If he does both, if he pushes up and lowers it back down during the complete downward and upward motion, how much total work does Justin do on the bar? The two things will cancel out. So I do have some more things that I wanted to do today. I had a little demo actually with this spring, which I will do next time. I'm going to release this on Wednesday morning. But just to finish up today, I wanted to quickly talk about tomorrow's test. So midterm assessment number 3, it's coming up tomorrow night. So remember, each online half-hour assessment is worth between 10 and 12.5% of your mark, depending on how many of these homework credits you earn. The lowest of the 5 assessments will be dropped. This assessment will become available on Quarkus to start at 8:10 p.m. tomorrow evening. So 24 hours plus another 8 hours from now. If you are registered for the alternate sitting, then you do the whole thing exactly 2 hours later, 10:10 p.m. If you don't do the assessment, you get a 0 on it. That could be dropped. The assessment is open book. So allowed aids include your course notes, the textbook, these videos, Google searches for static web pages, a calculator, Excel. You can use Python code if you want. It's all fine. However, you must work on the assessment individually. Don't do it yourself. You're not allowed to get help from other people, like a live people. Once you start, there's a 30-minute timer which will begin. The assessment will end when your personal timer runs out of time, 30 minutes, or at 8:45 p.m., whichever comes first. That gives you kind of a 35-minute window to do this test in. You can start it up to 5 minutes late and still get your full 30 minutes. You will see one question at a time in a random order. You must submit each answer by clicking next in order to see the next question. You will not have the ability to go back and change any answer after it has been submitted, so be sure. After you complete all 10 questions, you have to click Submit Quiz before the time has ended. I've put on 4 conceptual questions and 6 numerical questions. For the numerical questions, you will need a calculator or Excel or something running there to find the numbers. You should have a pencil and paper ready to do some rough work. I think that would be a good thing. All questions are multiple choice, and they're all marked automatically, so you get the mark back pretty quickly. So if it's 30 minutes and 10 questions, that's an average of 3 minutes per question. You can expect maybe the numerical questions might take a little more, like 4 minutes or something, but don't get stuck on a question and spend 6 or 7 or 10 minutes on a single question, because you will run out of time. The material will cover mostly questions and problems from chapters 5 and 6 of a Keen. But chapters 2 to 4, as we've seen, are important as well because we kind of build on it. Physics is by its nature sort of cumulative. There will also be at least one question based on your work in practicals 2 and 3A. So this is your reading assignment for Wednesday. I'm going to say good luck to you on tomorrow's test. And I'm going to turn off my recording and open it up to questions from the floor. And if I don't see you, have good luck on the test, basically, and have a good day today. Turn off my recording.